Today I am going to talk on materials and processes, and I will be giving a brief introduction on these things. And materials, when we talk about, we see around the matter, all the matter which is useful to mankind, that is called materials. And any process we use to shape or give a property to these materials for usefulness of the mankind, we call it processes. Okay, so we will be talking about all these things next to us. And the content of my talk will be like evolution of engineering materials, how the materials evolved through ages, what are different materials classes and processes, and the databases what we have from all the materials and processes. What is the how we can select these materials from these databases, and then obviously there are material innovations, new materials are coming up. So we will have a look on what are different patterns and paradigms in new materials development, and how these materials and processes are going to affect the sustainability of the environment and during the developmental process. And also, I will talk about a little bit on innovations in materials and processes, though there are a lot of things we do like steels, foams, additive manufacturing, thermomechanical processing. But here in this session, I would like to concentrate basically on spray forming. I will introduce this spray forming process as well as introduce you with the new materials which can be developed by spray forming. Am I audible?
Yes, you're audible.
Just check. I will do in between. So before we start with the real engineering materials, we have to understand what material and processes are. And I think the best way to look at it is through the food we eat. So here, the raw materials for our food is cereals, spices, and the vegetables that we know for vegetarians basically. And then using these raw materials, we cook it. We process it, and this processing, all the things we do during cooking, we call it a process. And finally, we have a product. We have a product in our thali here. Okay. And this product, how do we say that, how does it perform? So we have some kind of parameters like what is the taste, how costly it is, how nutritious it is, how does it look like. And there are so many different kinds of parameters to check the performance of this food we eat. So you can understand that we use raw materials, we cook it, and then finally make our food, and then we judge whether the food is okay or not. Okay, based on several parameters. Similarly, for engineering materials, we have materials, then we process it, then we get a product, and then we see the performance. So whatever engineering product we have around, we can think of that as a whole in terms of materials, process, product, and performance. Now we come to see how through the ages the material evolve. So here, if you see, in very ancient age, the major important materials were ceramics and glasses, which came through stones. Is my what do you say, cursor visible to you? Hello.
Yes, it is visible, sir.
Cursor is visible. Okay. Yeah, so initially we had stones, planes, and glasses, which are naturally occurring. Then we had straw and brick. We used to make that we can call composites. All these things were naturally occurring. Okay, with the time, when we found the bronze, iron, then the importance of these materials increased because we wanted to have more and more better properties which was given by the metals. And by the mid of 20th century, here you can see the importance of metals increased tremendously because they gave rise to many of the products which mankind wanted. And slowly, with the new technological development, ceramics, composites, and polymers, they started replacing the metals. And so their importance increased in the recent times. But why it happened? Because earlier it was the easy availability of the material and then intense requirement for the mankind that led to new developments. And right now we are in this region of technologically advanced materials we are going in. And that has led to a drastic change in the products what we see around. In the left side, you can see that it's ancient processes and ancient products, and in the right side, the modern products. So all this happened due to these developments. But we should look at these two phenomena, two materials. Here you see blacksmithy and clay pottery. They are used even now, today in modern age. We do not know whether these developments, which are there since ages and being used today, was it Edisonian effect of development, or was there any scientific development? That we are not sure. Okay, but today, just for example, we know that why in blacksmithy the material is heated, then shaped, then quenched, all those things are done. But earlier we might not have understood, and that might have been based upon the trial and error processes. And similarly with clay pottery, as you are able to see here. If you look at the development of materials through the ages again, here you can see in prehistoric times, many of the materials we used was actually naturally occurring, like metals, gold, for example, then ceramics and glasses, and the natural materials like wood and fair pine trees, whatever material used to get from the plants or from like bones, shells from sea, stones, all those things were used. Slowly, new metals like when we got bronze, iron, the new metals are added into this. Similarly, new developments in ceramic and glasses and some new composites of naturally occurring fibers and other things took place. And today, if you look at, then a whole gamut of materials is there from very low density materials to very high density material, and strength varies from very low to very high. So we have a lot of materials developed today, and whatever product we want to make, we have to select these materials from these products. But today, the whole humanity is searching for new materials where we can reduce the density and the strength increases. So this is the region, this triangle, what you are able to see here. That is the region we want to go. We want to reduce the density and increase the strength in this case. So we can see that materials can be classified in three different ways. One is metals and alloys, then polymers, then ceramics and glasses. And the fourth one is composite. So we can use metals and alloys and like steel cord and tires, we know. In tires, steel cord is used with polymers, rubbers basically. Then we use polymers and glasses and ceramics like carbon fiber reinforced plastics, glass fiber reinforced plastics. Or we can use metals and ceramics like ceramides. All these things are possible. And the major thing is that these composites, they are the mixture of two or more phases like metals ceramics, and ceramic composites can be there. There can be different matrices like metals matrix, where the major phase is metal, and we can use ceramics or polymers in that. Or we have polymers, and there you can use ceramics and metals. So we can use these materials. You can make a component of that, which can give rise to the properties, which are the combination of the properties obtained by different constituents of body. Nowadays, there are other materials, we call it hybrid materials. So a composite can also be termed as the hybrid material. Then sandwich materials, two different metals can be sandwiched together and given heat treatment. You know, the cells have structures of this layered structure, metal and ceramic, and this is what ceramic and polymers, and this is how you can make like nickel or nickel aluminide, titanium aluminide kind of sandwiches, metallic foams, or lattices. We will talk about this later, or segmented structures. All these things can be made using different techniques, and we term them as hybrid materials. Recently, there is one new material called high entropy alloys. So let us see first the conventional materials. For example, when we talk about steel, so major component in that is iron. So here you can see if this is the iron end, so the other alloying elements C, B, or D may be very small in amount, but major will be A. So generally, this is how conventional alloys were made. But as you increase the amount of the other element B, C, or D in that, then there was a possibility, there is a possibility of formation of intermetallics, and which destroy the properties of these alloys. Okay, so that restricts the possibility of using more and more alloying elements, even though we understand that uh, these more of alloying elements can give rise to better properties. So that was a limitation. Basically, remained unexplored as conventional alloys, and suddenly in 2004 there was a publication by Professor Brian Kainter, and he basically used to work in the area of metallic glasses, where people used to put large number of different elements, and we call it confusion principle. And using that, they used to design glassy materials, bulk glassy materials. So I think that led him to try this 20 elements together and melting them. But what he found that after that, the major fraction of that material was with single phase FCC with chromium, iron, manganese, iron, cobalt, and nickel. So this gave a very good indication that such materials with very large amount together, large fraction together, is not only a major element as we saw in conventional alloys. We can make a single phase material without intermetallic phases in that. So that led to the discovery of high entropy alloys. From Japan, Professor Y.A. also was there, contemporarily working with Brian Cantor, and that led to this discovery. And if you look at the properties of these materials, they are really very unique in the sense that here sub-zero temperature properties are tremendously high, you can see. The elongation as well as ultimate tensile strength. Or these are the steels we use generally today, but high entropy alloys, they have very high strength as well as ductility in this case. And high temperature applications also you can see. These are the properties at high temperature. So these are new class of materials, and I think within the 17 years of development, we have a long way to go for such materials. And there are different applications in research for such materials like engine materials, light transportation, functional coatings we can do, because it depends upon what are the composition and how we can use them. So one thing is very clear that if you are in the, as I mentioned you earlier, if you are in this region, then the possibility of designing of new alloys is very small. But if you are here, so you have a large possibility of designing a large number of alloys. So if you look at the opportunities or challenges in this area, then you can find that if the judicious alloy design can be done for different properties, and we can try to educate ourselves to genuinely design the compositions based on our requirement. Okay, and major challenge is that if you have so many possibilities, then if you go by trial and error, how much time you will take to reach to optimize composition. So that is the major thing we have to be careful, and people are working in this area so that using artificial intelligence, machine learning, ANN, or calculation of phase diagrams, they all are doing it, and by that they they are coming up with new compositions of these alloys. Nowadays, a new area has come up like architecture materials. We know that in the left side, if you see, this is the beak of a hornbill bird. Inside, there are different structures you can see. And this is the bird wing bone. So inside, it's a total bone is low density, but inside there are different structures with this ligaments. So what makes them happen, and how they support the whole structure of the bird? So it has to be light and it has to support the load. Similar, and this is the naturally engineered materials. So using this, there are different ways like topological optimization. You have this material. Can you reduce the density of this? OK, we can reduce the density by taking out the materials from this or putting in more of air inside that. So you can reduce the density. Like that, here you can see if different elements, the thickness of this is reduced, you can reduce the density of this. And just say this is a lattice, and this lattice can be changed to a different lattice. And if you can combine different lattices, then you can have different properties. For example, a body-centered cubic lattice and a face-centered cubic lattice, we know what is the effect of all these things in real material world. And if we can combine these together in a long range, then we can see the effect. And based on the new development in the area of additive manufacturing, basically, such kind of a structure, such kind of structures has become easier, and people can easily make these. And this is why, with the advent of additive manufacturing, this architecture material have taken more of importance in these days to make light materials. Here you can see these are the light materials. And for example, if you have a pure nickel here, so the density is very high. Now, if you want to reduce the density, what you can do? You can play with the structures, as I talked about topological structures, or density changes, or microstructural changes, and you can end up with this material in this region with low density. But here, just say this is the area you are going like this, for example, and you can have materials in this region. But now with nickel, with this strength, you can have a wide range of properties. For diamond, you can have wide range of properties. So this way, you can end up with low density but high strength. Or you can design the system such that they can give some diagonal properties in the material. So these are things, these are the materials people are looking at with very high promise. And to do that, we generally select the base material like nickel or diamond, we say, and we do model. We model the strength and stiffness of such structures, and using different functions of architecture and loads. And then once we do that, then we can apply some constraints, whether we can manufacture it and what geometries are possible, what would be the effect of this thing on environment, all these constraints we put, and then we verify the validity of models. So we have analytical model, and then we go to FEM packages. Many of the FEM packages are available today. And then we model that through FEM and see what are the properties. And finally, we have one objective function. What objective function means? If we design any material, so what are the parameters which need to be maximized in that design? And that function we derive, and that gives rise to our design constants. Okay. So overall, we can say that there are two kinds of material, two types of materials. One is structural materials, that we call it load-bearing materials, where the key properties are elastic modulus, yield strain, and something like that. Corrosion, wear, these also can be considered to be in the area of load-bearing materials, because they deteriorate the properties of the materials. And similarly, the other materials are functional materials, where optical properties, electrical properties like thermal or conductive, resistivity, other things, magnetic properties, all these things are considered in these cases. What purpose they solve? For example, just here there is an aeroplane. This one. This is. It should be like this, but if it is not very stiff, then it will go like that, and it has to be stiff so that it doesn't bend like this. It has to be strong, so it should not deform like this, or it should be tough, or it should be have low density, because otherwise it may sag like that. So a material with mechanical property requirement can be well defined, that what would be the strength, toughness, or density, other things. Similarly, we can have different functional properties of these materials, which we can think of. And then we classify the material properties, which is basically required for designing any product. So, for example, designing any product and making it economics is a very important thing. Then these are the properties we talked about. Then ease of manufacturing, whether we can join it or not, we can, what is the finished properties, surface finished properties we want. And aesthetics also play an important role. And what color, texture, and what kind of feeling, when you touch it, what kind of feel you have to have. So all these things, they determine the product design and development along with the materials and selection of processes. Okay, so now you see here, these are the structures we generally see around buildings, bridges, windmills, railways, aircrafts. So there are n number of applications of these materials we see around them, see around us, and these all applications require some development, some kind of development in new materials. And similarly, in transportation, we are really concerned about the transportation industries, where you have to have low carbon emission, reliable design, then low cost, efficiency, you have to ecological, it should be ecological because you should not destroy the environment. So a lot of demand on transportation sector. And so far as safety is concerned, here you see different parts of a car require different kinds of materials. And the major thing is we want to reduce the weight of our automobiles. So we want to have better properties of materials. We want to have high specific strength so that we can reduce the amount of material we have to use in our cars. So they become light, but we do not compromise with the safety of passengers. Similarly, we know that crude oil, it is transported from very long distances. For example, in Siberia, we have crude oil reserves. If we want to have uh, crude oil transported from there to some other countries, it has to be very tough because the temperature is low. So if the temperature is low and we have to transport the material, so it has to be tough first of all. And also, if we want to increase the efficiency of transportation, we have to increase the pressure of crude oil transfer. And to withstand that pressure, the strength of the material used in pipelines, that has to be high. And in such cases, new developments in line pipe materials, now we have reached to around X120, very high strength material with high toughness. So these are the areas like wear resistant materials and line pipe steels. These are the areas which demand so many different properties. Properties can be summarized as this. Strength to weight ratio should be very high, toughness, fatigue strength, machinability, impact strength, wear resistance. I can tell you that today the demand on material is tremendous, and this demand has led to large amount of research possibilities on that. Anyway, it depends upon what economics lies go along with that, but possibilities are tremendous that it can be achieved and we can improve the material properties. So what we can say that a product if you make, so generally we know that these are the materials we have. With the databases, we know that so many materials in steels, aluminum, magnesium alloys, copper alloys, they are there. Even then, we know what are the functions of the material, if functions of a product. So there has to be a correlation between the material we use and function we perform using those materials. So in between there are different things like what property it has, what structure it has. So structure determines the property, and structure comes with the process, and the process determines what kind of shape you can give to by using those processes. So all these things are interlinked. So from materials, if you go to achieve the functions you think for your product, then it has to have all these four, it has to pass through this, and these have to be optimized to get the desired function of the product. Okay, and we know that we have data. For example, a material can be ceramics, different families of materials can be ceramics, glasses, metals, polymer, elastomers, or hybrid materials. And in that, if you take metals, there are different alloys. And in different alloys, for example, if you take aluminum alloys, there are different alloy designations, subclasses of this. So what I want to bring it to you here is that we have the databases available for different materials. And for example, this material 6061, we know the density, thermal property, electrical property, everything, all things are documented. Now, if you want to go to make a product, then we have to use all these data to design our product. Okay, and metals, ceramics or polymers, we know composition and processing. They are going to determine the structure, property and final performance. And similarly, the way we have materials, we also have a taxonomy of processes. For example, processes we know that joining, shaping and finishing. These are basically giving shape to the material. And in shaping process, we also have some kind of secondary processes which can give you the properties. For example, if you develop a steel, the steel has to be rolled through a thermomechanical process, and giving the shape is one thing, but at the same time, steel has to have some given property. So a close control of thermomechanical properties is very small, very much required. So with the process, you get the shape as well as the properties. So it's very ingenious selection of such processes need to be had for a product. So here is just primary shaping processes. You can have casting processes, molding methods, deformation methods, for example, rolling, forging, and drawing. Rolling I just talked about for steels. Then powder metallurgy methods and composite forming and special methods. Nowadays we have additive manufacturing, different kind of additive manufacturing you have. Then secondary processing, you go to machining or heat treatment, and then joining and surface treatment, and finally you get the finished product. Here are just, I think I should not go in detail of these things because you can always find out that what these processes are, like sand casting, injection molding. Stereolithography is a very old technique, and die casting. I think you all know about this, and you can read in the textbooks also available. And I go to materials and process selection. Now we know that we have the data. We have the data on materials, and these data, how can they be used to very efficiently select a material for my product I have planned. So this is called materials and process selection. First of all, what material, and second is what process. So the taxonomy of materials and taxonomy of processes is available. For example, these databases, and these databases need to be used to select optimize material and process. So here you see, design is the process to translate an idea or a market need into an embodiment from which a product can be manufactured. So that means if you get an idea of a product and you want to launch in the market, so you have to design it first. Design into an embodiment means you design it, and then you think of concepts, and once concepts are ready, then you choose from different concepts and you give the property, material, and all those things. Then you say we have an embodiment of a product. And the stages in design of manufacture, design to manufacture requires selecting materials, of which the first stage is a material of which the product should be. And it also requires feasible and cost-effective process for making it. Definitely, as we talked about earlier. And the choice of material cannot be made independently of the choice of process. Because processing, just for example, a ceramic cannot be rolled, for example. So you cannot choose rolling for ceramic. So material had to be chosen along with the process. Although material choice is dictated by the design, but sometimes discovery of a new material leads to a new product design. And this is what we were just saying, that if there is a requirement of high temperature withstanding of a product, and high entropy alloy can give very high stability at high temperature, then that can be used in that area. So you can find out some new product design based on a new alloy developed in high entropy alloys. Okay, and what are the drivers for these materials and processes? There are many new materials, different types of materials. There are new manufacturing methods available for us, and there are many materials which are being researched on, and with some new things, properties improving. So definitely a product which is using that material can be modified with the new material. So entirely new design configurations are feasible. So you start searching for a new material for that. Similarly, there are so many things, and why it happens, you know, that here you see this is a kettle used long back. Why it was used? Because it had to be heated, so it had to be metallic earlier, and this teapot. But now heater is inside, so you need not have to have this metallic. It is from plastic. So there is a change just because now you have a different configuration of your material, your heating system. Similarly, from cutting to additive manufacturing have transferred. Now, you see, camera, earlier we used to have this, and this transferred to this, and now we are here. So the changes are taking place, and similarly, your product is also changing. So, due to rapid development of materials technology, material selection is both critical and complex. And what are the processes for material selection? Why do we do that? First of all, why should we select a material? So to make full use of possibility with engineering materials, to avoid unnecessarily expensive structures, to avoid failures. If my material we are using in our product is failing, then definitely we have to be very careful that we have to use new materials for that purpose. And to respond to environmental regulation, you know that today, due to a lot of sustainability issues and environmental degradation, a lot of regulations are coming from different governments. So you have to design a new material or select a better material from the available lot, or to increase the reusability of materials. Now we are shifting, the whole world is shifting towards circular economy, and this requires that materials should be reused, recyclable. Product can be reused, or the material we are using is efficiently recycled so that you don't depend upon the natural resources more and more. Then better. When you design a new product, you develop a new product, or you want to re-engineer the product with a new design, as we just saw earlier, then you require different material, or your material is failing time and again. And who does it? Basically, the engineers, design engineers, in collaboration with the materials engineers. They have to sit together and decide that what material, what processes have to be used. I think am I audible?
Yes, sir, you are audible.
Okay. These are the consideration in material selection. I think we already have done it. So basically, what I want to talk about is product shape. So shape can be given by certain processes. So if we want to make sheet, strip, or plate, you generally go for rolling mills. Or if you want to go for different shapes for example, automotive parts, then you go to forging, or even very complex shapes, you go to casting. So there are different kinds of shapes. So that gives you that what kind of material you can select and what processes you can select for these purposes. And then aesthetics and cost we just talked about. So what are the selection strategies? First of all, so you have inputs. When we design the product, what we do? We say that what features my product should have and what are the design requirements, what is the property we should have, what functions it has to perform. And based on that, you select a material and process as an output. Okay. And in that process, there must be a transfer function which says that, okay, you want to have these inputs, these are the requirements, and so you have to use these selected materials, and that function strategies has to be adopted like that. So strategy one, where you know all the properties, we call it measured attributes. So you know all the properties here, and uh, this gives you free speech, means you know the properties and whole gamut of processes at your doorstep. Now you have to choose from them. So you are free. You are free with the quantitative values of the product and material and processes. So your freedom of choice is more and more. Okay, so you have the possibility of innovation there. Second is a questionnaire-based strategy. Means there are some expert available at you, and they say that okay, for this product you can use this. So what happens? You have possibilities with you is less and less, and then only known solutions you will have. You will not have an open solution. Whatever expert knows, he can guide you to get that. Okay. Please mute your. Please mute your. Please mute yourself. Who is that? Yeah. And then there is a third strategy where you depend upon the previous applications. So you have a product and you go to see that what similar kind of products are there and what materials and processes they use. So there you don't have any much of innovative way. You return with the cases with features like that of the present problem. So all the people use that and we also use. Anyway, first strategy is the best strategy in today's time because that gives you the possibilities of innovation. Now, there is a cost of product development. How to determine, for example, in the beginning, when you conceptualize a product, you make a preliminary design that my product should look like that and it should perform these functions. So here you will have very small cost to this. You will not, since there is no product as such and you are not processing it. So cost incurred will be very less, but your commitment will be very high. Due to high commitment to the market as well as to your organization, this cost plus technical commitment is very high here. So, and knowledge will be less because you are still conceptualizing it. So knowledge will be less, and slowly as you start designing the design detail and developing it, and then you make prototype or construct it. So as you go in this direction, so what happens? The knowledge increases as well as the cost incurred on the organization or on the individual also increases. But in that way, your knowledge gap starts decreasing as you go on this side. So what happens? Generally, we should have low cost here, low cost incurred, but this knowledge gap should be reduced. So what to do then? So this is why most of the people today, they are using different softwares, different, just say artificial intelligence, machine learning, all those things. So beforehand, even people are using digital machines. To, for example, if we design, you want to design a motor, so they have digital motor and all the experiments they do there, so that they come out with all the knowledge in the beginning itself without incurring a lot of cost to that. So they can reduce the knowledge gap and without any cost. So this is what people are doing today. And we are moving in that direction. I think you understood what I want to convey in this slide. So, what are the tools and material data we have? For example, design tools. Generally, what happens that when we make a design product, so we know design requirements, we have a concept, then we go for embodiment, then some details of the materials, and then product specification. I come to that how we do it. So what happens that in all the design tools are there. So initially we make a concept that what kind of product we should have, what it should do, and all those things. But after that, that is not enough. So what we should do, we have to have some possibilities. What concepts it should have, how it will work, and what kind of different materials it can use. So doing that, and then after that you make a prototype of that, and based on this you make a full product specification. And what is the material data you want to have in this case? Here you see we have designed for manufacturing software, FEM modeling we can do, where we can have component modeling, material selection software we can use, simulation methods we can use here. All the things we design tool we will have before reaching to the product specification, that what kind of material it should have, what kind of processes it should have, what are the functions it is going to perform, all those things. So here in the concept level, data for all material you have, and generally you have low precision and detail because you are left with large amount of possibilities. But once you make the concept and go to embodiment, then you leave out some materials, because in that concept some materials do not fit at all. So now you have a subset of material with higher precision and detail. Once you have these materials, then you go to make further details, like what kind of property you want, what kind of elongation it should have, whether it should have corrosion resistant or not. So similar kind of thing. Then you again go to more fine details, and then highest precision of and details of the material you can have, and that will determine the product specification. Okay, and how do we do that? So you have all materials and processes, and you are sitting with a question mark that how should it go for that? And finally, you want to have a final selection of material and processes. So first of all, you do one thing, that you go to function. What are the functions it has to perform? What are the constraints it should have? Constraint means some constraints are non-negotiable. For example, you put a constraint that you don't want to use ceramics in that, or you put a constraint that it should have a mechanical property not less than that. So these are the constraints which are non-negotiable. But some constraints you put and you say that, okay, we can negotiate. Just say ductility of the material should be in between 10 to 15%. If 11% is there, that is okay for us, or even 14%. So no issue. So these are the constraints we put on the material. And then objective. What should be in the beginning? I told you about the objective function. So, that function should be maximized or minimized. So what objective function has to be there, and what are the free variables? Means you don't free variables means you don't care for those parameters. Okay. So once you screen the materials based on that or processes, so you apply all the constraints on material attributes, compatibility of the material with the process and shape, and similarly process selection also you can do. Then once you do that, then you get a subset of materials and processes, and further then you go to performance metrics and to develop an index for making ranking. So what you do that once you have these materials, and then you go for performance metric objectives and develop a rank. You rank the material based on their performance. And similarly, you can rank the processes also. And once you rank them, then what happens? Then again, you are ending up with a subset of materials and processes. Here, once you get a further subset, then you are left with a selected matrix. Now, out of these selections, you want to go to experts and previous case studies. For example, you are left with 5 materials which can be suited for a product. Then you go to literature, you go to market, you go to expert and find out. Now we are ending up with 5 materials. What is the best you can choose from them? And similar for the processes. And once you do that, then there is a final selection of material and processes. And we do have a lot of materials, a lot of softwares which can help you in material selection. I think I am going very slow. So, yeah. So now we go to materials innovation. Here, this is a picture you see in 1900 in Fifth Avenue University. There is no, all are horse-drawn carriages here. There is one car here, you see. In 1913, there are a lot of cars and there is only one carriage here. Okay, so in 13 years in the same street, you can see the development. That means more than 100 years ago, the pace of development was so fast, and today also this is happening. So we have to be very careful that things are changing and we have to keep pace with the changes happening around. Okay. For centuries, new materials took long time to develop. And for example, the food we eat today, I think 1,000 years ago, people were eating the same thing. We have not added any new food up to now. Anyway, some combination definitely. Okay, so what I mean to say is it takes long time for material development, and we have to speed it up, particularly when we are dealing with the regulations on environmental situations. And definitely, if we have a large bulk of material databases, it's very difficult to select from there. So we have to make educated guesses from this. And this technique is called materials informatics. And I think we have to go faster here. Generally, any material development or process development, it takes a route. For example, you have equipment, and we go to processes, microstructure, properties, and performance. And what happens that in one way, you know that your product has to perform in such a way, and then you go back to the list of properties of materials you have and macrostructure you have. So this is called science-based methodology, where you know that what performance your product has to have, and we call it inductive inference. And basically, the science-based techniques are based on inductive inference system, where you decide that what performance you have to have. Okay, and then you start choosing from this, and you based on the goals and means, you think inductively and decide that for this performance, based on the databases, what process equipment we have to choose. But the other way, that you decide the goal and start with trial and error with this as a goal. Okay, so here each and every work you do, you see the cause and effect, and then finally you reach to your performance. So basically, the difference is in one case you have defined the performance and you go with the databases. And here you discover the data and finally the application on the way of your research. So this is called a predictive method, and this is called optimization in design method. So when we talk about material selection, we go to this, and when we talk about the discovery, you go to this. So here we can say that the data is very important. We take the data from literature and experiments, and we try to correlate these data with inference engines. So today we have artificial intelligence, machine learning, we have ANN and different tools. Using those tools, we come up with a correlation between the data points we have. Data is very important in this. And then we develop a theory, and once you make that, then you reach to the knowledge base. So data today is one of the most important data on materials and processes, more important than previously what we had. Previously, we used to base our decisions on testing, but today we have to base our decision on proper analysis. So this is a difference between the previous way of thinking and today. And these are the innovation infrastructure that we have to have computational tools, we have to have experimental tools, as well as extensive databases for the material discovery. Okay. And materials innovation paradigm I talked about. So if you look at earlier, we used to have do experiments, and all our discoveries or any knowledge base were depending upon the empirical sciences. And with the advent of thermodynamics, for example, we started looking at these experiments from the point of view of thermodynamics, and then we use certain kind of prediction in that. But it was very difficult to predict that time because the computer speed was very slow. But as the computer speed increased and computational facilities, they started functioning better and better, like ANN, molecular dynamics, density functional theories. They started giving more and more data to us, and that helped us in designing new materials or new experiments also. But today, we are driven by the data. So we call it big data, and in other arena, we say data science. So data science is going to have a very definite role in materials and process discovery in the coming days. Discovery, I'm talking about, not the selection. So discovery new materials can be obtained by using data, because that correlation was very difficult to make earlier. Now we can, using the data and the computational tools, we can have better correlation and therefore new design of materials. Okay. And I think I will skip some of them because it seems, yeah, the point is that how data is generated. Generally, data availability is very scanty because it's a patented data points and data, and people are not really sharing this data. So what happens that you have to develop this data by yourself, or there had to have a consortium who can think of developing data and supplying at one place, like ICAME. Integrated computational materials engineering is a subject today of high importance. So what people do is they try to make small samples today, and small samples with a different composition and very small samples. Here you can say these are the descriptors of material. High throughput means high throughput descriptors I explain first. High throughput means development of material at small scale and data generation at a very fast rate. This is what we mean by high throughput thing. And descriptor means once you develop large amount of materials, then how you can say that this material is good or bad. So we have to have descriptors like what is the hardness, phase constitution, thermal expansion coefficient, if you do extrusion, so what is the extrudability, all these things we can do on small samples. So first of all, we have to develop such systems by which we can develop the data very fast. We can generate the data very fast on small samples. So how to get the small samples? You see, these are different composition cast materials. You roll it, for example, with different compositions, and then here stack, homogenize, and do cold rolling and annealing. So what happens? All these sheets, there will be diffusion at the interfaces. Now you can cut small samples from different compositions. They will have different compositions, and these compositions you can use to characterize. So you in such a system, you can develop or generate data at a very fast rate. And today, with the laser additive manufacturing process, here also you can develop data faster, different powders of different composition, changing the flow rates. You can develop different alloys with different gradients. For example, different grade A and B, different gradients. You can choose different materials here and find out the properties. So what you get out of it is you get the composition and the properties, all the descriptors. So those data you can use, you can feed in the data system, and that can be used by the computational tools to come with a better material. So that is how it is done. Now, we go to sustainability. I think this says that if we have a raw material and you want to reach to a product or a product, then you have to go through a manufacturing cycle. And this manufacturing cycle requires labor, power, tooling, and machineries. And this leads to a product and wastage, definitely. So what we do actually, we using manufacturing cycle, we are adding some value to the starting material, and just say this is 1 rupee, we are adding value with 2 rupees, and the process part, which is product, we get 3 rupees. So all the processing techniques what we use, those are basically leading to the value addition. And what we think of it, any manufacturing cycle should be faster, better compared to the previous one, and it should not be costly. But today we end up with one more constraint, that is manufacturing should be sustainable. What we mean by sustainability is sustainable development to be defined as a development that meets the needs of the present without compromising the ability of future generation to meet their own needs. That means we should not destroy the environment where we are living, because we are living because environment is okay. So next generation should have better environment they can also live. And that is the whole purpose of sustainable development. And designing for sustainability requires large number of thought processes, like what is the functionality of the material, I mean durability, how easy is to use, how reliable, how to upgrade it, resource utilization and economy. For example, this is more important so far as sustainability is concerned. It should be whatever manufacturing you are doing, it should be energy efficient. Material should be utilized to the fullest. The wastage should be low. Operational cost, training cost, all these things should be low in that. Okay, so similarly, I will not go in detail of this, but I just wanted to bring to you that recycling, environmental impact, societal impact, all these things have to be considered whenever you make a product and you decide on a manufacturing cycle. If you are not doing, then it is a harm to the society as well as the environment. This is why governments want to regulate it, because humanity, if they do not understand by themselves, it has to be regulated. And there is in this process material efficiency. So if we want to be very sustainable, then we should have a good material efficiency, which refers to a system of production and consumption characterized by a closed loop of materials and energy flows. What it means? Closed loop of materials. That means directly reduce material production. So what to do that? Then improve material yield ratio. Material yield ratio means the performance given by the material should be better, and designing products with less material. So this is what people are saying, that if we have high strength steels, advanced high strength steels, then the material required to make a similar kind of automobile will be less. So this is what aim is, to reduce the material production by reducing the material requirement in the product. Avoid disposal and recycling. So we have to not to dispose it, but we have to reuse, we have to recycle, we have to be able to remanufacturing the material. So we should not be very much dependent on the resources for extraction and other things. So whatever material we have extracted, that should be used time and again. Why it is so? Because in extraction, for example, today steel is one of the materials which takes minimum energy per ton for production. Okay, aluminum takes now 6 times more energy than steel production. Steel extraction, I should say, from the ore to the steel, iron. Okay, so that way we have to be very careful that we should not be using our natural resources very much if we want to be sustainable. And this is just say that today we are moving to linear economy, where we use the natural resources and finally we dispose of the product as a waste. But circular economy, it suggests to us that any product, it has to be reused. Nowadays you see that automobile is the market of used automobiles is increasing day by day, and remanufacture, reuse second-hand car sale, for example, and remanufacture means the old car you are taking and refurbishing it so that it can further be used without going to the new material requirements. And second is recycle. Take the material and recycle in cheap way so that you have more production of material and you do not depend upon the natural resources. So these are the things we have to take care of during our production. So with this, I come to the end of the material and process introduction. Now I go to the process innovations, where I was talking about spray forming. So I think I am left with around half an hour. Dr. Mishra? Dr. Mishra?
Yes, sir. Yes, sir.
Am I left with half an hour now?
Yes, sir. Little more than half an hour.
Okay, so in this period, I'll be talking about spray forming. Now I will come to the technical part of it, and I would like to suggest that with process innovation, there might be some elements of physical metallurgy in this, like microstructure and all those things. So be careful and try to understand what I am talking about. Up to now, it was very general on materials and processes. Okay, so spray forming. First of all, I should start with the aluminum silicon phase diagram here. And in this case, this is eutectic phase diagram. And if I want to use aluminum silicon alloy, at more and more silicon, I know that more the silicon in aluminum alloy, the wear property of the material will be better and better. But the moment we go to higher silicon content, the solidification range from liquid to solid, that is very, very large. In that case, the first phase which starts forming here, the moment that liquid comes to this temperature, silicon size becomes very large. Okay, if the silicon size is very large, that material cannot be used for application. So what happens that somehow we have to do something so that even after using silicon in larger amount as an alloying element, we can get smaller silicon size in the aluminum matrix. But generally, the casting processes lead to slow cooling rate. So if from this temperature to this temperature, if you come, then if a cooling rate is very slow, the silicon gets enough time to coercion. So it becomes very large in size. So that casting process doesn't give the possibility of using more and more silicon in that. There are segregations. So the limited alloying content. You cannot go to high silicon content. You have to be staying somewhere here. Then you get coarse structure and intricacy is not possible in casting process. Okay, so in such a case, the microstructure what you get is something like this. So if you have silicon 6.5%, then you get a dendritic structure. In S-class material, if you increase the silicon content to 18%, large size of silicon it is formed. So this is not usable in any application where we want wear resistance. Okay, this is aluminum with 25% of Mg2Si alloy. Here also is 200 micron you see. So these the precipitates of Mg2Si is very large in size. Okay, so where we want actually refined size of these alloys for good applicability in the application. For that purpose, people used to apply high cooling rate. So you might be aware that melt spinning and high pressure gas automation are two processes where you can get very high cooling rate. So I would here you can see melt spinning is you have a liquid. This liquid, this is rotating copper wheel, and this liquid when comes here, then this is a thin layer of around 50 micron thin sheets are going away. So the moment it is touching this copper wheel, water cooled copper wheel, then this experience very high cooling rate, and then the chances of getting silicon larger is 0. Okay. Similarly, in gas automation, what happens that there is a liquid and you have a nozzle. Here, there you get some inert gas jets, or even you can have wear, and this disintegrates the liquid stream in very fine droplets like this, and these droplets under the effect of very high velocity gas jet, they feel very high cooling rate under the convective heat transfer because of the very small size of droplets. So the surface to area, surface to volume ratio increases, and that increase in surface to volume ratio gives to a very high cooling rate. And it is not that high as you get in melt spinning, but it varies from 10⁻³ to 10⁻⁶ Kelvin per second. So these are two processes which are used for rapid solidification. How they used to do it? To use this material for application is they used to chop the seeds, pulverize it, and then use powder metallurgy method, powder consolidation and sintering method to consolidate in a part. Similarly, these rapidly solidified powders can be used by a powder metallurgy route to make a component. Okay, but all these things require a lot of process steps, and handling of powders was very difficult in those times, and pulverizing and other things, they were not good for health also. Okay, so there is a spray forming process. Here in this spray forming system, it has a crucible, it has a turn dish, as in gas atomizer, it has an atomizer, there is a substrate. So you know that same thing was used earlier. In this case, liquid stream coming, then atomizer. So same up to this, it is same as gas atomizer, but now we have a substrate here. What it does, you see. So similarly, once the stream is disintegrated into small droplets, the droplets are propelled towards away from the automation zone here, and this is cooling, this is cooled. So there are definitely not a mono-size droplet, there are different sizes of droplets, and the droplets experience different cooling rates. Okay, so if they have different cooling rates, obviously very small droplets will be solidified. Just say, for example, here if we have a small droplet, okay, a small droplet cooling very fast. So by the time it comes here, it will be totally solid. Okay, now there is a still bigger droplet. So it will start solidifying, but it may not be fully solid by the time it comes here. There may be some still larger droplets which may be in fully liquid state. So what happens on the substrate? You have solid particles, you have semi-solid particles, and one fully liquid particles and droplets. Okay, so when they come here, so what you get here is a liquid pool with large amount of solid particles as well as all those solid parts here. This is semi-solid actually. So solid parts also will be in the liquid pool and moving here. So this deposit, what you are getting, becomes very good for grain refinement. All these small solid droplets or the semi-solid solid part of semi-solid droplets, they will be broken because the droplets when they are coming, they are at a very high speed. The moment they hit it, they are shattered, and all the small solid parts of this will be shattered in the liquid pool, which will act as a nucleation site for the development of the microstructure. So this is how spray forming works, and this gives rise to very high refinement in the microstructure. So this can be replaced. This is replaced for casting process where you are limited with the composition. So here you can use different composition for grain refinement, as I discussed for aluminum silicon alloy. So this is how it looks like, and okay. So you see, this is a continuously cast copper alloy, and this is spray form copper alloy. So you can see the difference between these two in microstructure, the uniformity of microstructure as well as the refinement. So this is what spray forming is all about. And here, this is an alloy of aluminum, copper, iron, chromium, titanium alloy, and this is the structure. This is the base, and these are the intermetallics. So this is slowly cooled cast material. Now, if we do a spray forming of that, then here you see spray forms material. This is 200 micron, and this is 50 micron. So you can see that what is the amount of refinement you are getting for this small second phase. So spray forming is very efficient in designing new materials with the refined structure. So any material which is not any material which is not suitable for casting process can be processed by spray forming, and you can get the desired properties also. So here, when the workshop is on processing of novel materials, what I say, the material is old, but the processing is new, so you get a novel material here. Okay. So what we do generally in spray forming, we use nozzles. Here you can see this is a nozzle melt, and stream is coming, gas is coming and interacting with the liquid at a very large distance from here. So gas loses some energy while it is coming from this place to this place. So efficiency of automation is not very good. But in this case, gas is coming here, and what happens that gas is coming in this direction like this, and liquid is coming like this. What happens? The gases here, there is a zone, a low pressure zone, and then gas starts coming like this. So the liquid coming here, it diverts in this direction like that. It goes like this. So liquid film will be here, gas will be coming here. So this is the thickness of liquid which will be interacting with this gas, and the interaction angle is around 90° here. And liquid is going in this direction, gas is coming in this direction. So the efficiency of automation of liquid in this case, with this automation nozzle, is very good. And so we get very fine powders, fine droplets by using close coupled nozzle. There are some variants definitely with spray forming. Here we call it gas automation and spray rolling. So here the spray is on two rolls, and rolls are making a sheet out of this, so that any porosity or any defects in the process can be reduced, and you get very dense sheets here. Second is impulse automation. Here there is a process where you have a perforated disc here. This is liquid and perforated disc. The perforations are of a size of around 50 micron and or less than that. And then the pulsator, this pulsates, and then droplets are coming down, and they can be collected on a substrate as a deposit. Also, there is centrifugal automation. The liquid is coming down. This is very rotating at a very high speed, and as the droplets come in, and stream comes in, they are divided into small droplets and they deposit here. So if you want to make a tube, you can use this technique for making a tube. Okay. Similarly, as we talked about rolling, spray rolling. So here this is the system of spray rolling, where this is liquid, inert gas is coming from here, changing into spray, and the spray is rolled, and finally you get a structure like this at different places. So highly refined structure you can get. This is the structure, aqueous structure at this point. Once rolled, you have this structure. So this is and how it is done. And manufacturing using two sprays. This is melt one. Just say if a melt one, you spray it, there is a deposit. And what you can do is you can have a second melt spray also. So you can get bimetallic materials in this. And these bimetallic materials can be further rolled to get very dense material here. So you can see that after rolling this material, this interface can be modified, and once you do some heat treatment also of this, after heat treatment, you can get bimetallic materials. Okay, now I come to spray forming of composites. I think many of you would be aware that metal matrix composites by casting route are made by ester casting route. There is a liquid, and this is a furnace. There is a crucible. In that crucible, you have a liquid and one impeller here. And then you put second phase powder like silicon carbide or nitrides here, and then a very high speed of rotation of impeller gives rise to the vortex, and this material goes in. But there is a problem that if you have very small size particles, then surface to volume ratio is very large, and due to surface tension, they are mostly coming to the top of the liquid. So and small size, they also give rise to clustering of particles. So these are the problems with the casting process. So incorporation of small size particles is very difficult. And since casting is at a very high temperature, then there are interfacial reactions at the interface, and there are segregations. These are the problems happens with the metal matrix composite made by casting route. And these are the microstructures you can see, which is mostly not, if the control of the parameters are not very efficient, then such things may happen like velocity, agglomeration, cracks, during rolling, other things. Okay, so in spray forming, what we do is there is a dispenser where this is a feeding screw. We put the powders of powder storage, and with the screw, this is the gas inlet. So this is closed chamber. This is full closed chamber. The gas is coming from this side, and here the powders are going in a funnel, and then gas and powder mixture is coming out. Okay, and this mixture is fed in the nozzle system here in the spray forming. So what is happening that is powders and the gas goes in atomization zone along with the liquid. So and the issue of any issue of agglomeration will not be there, and any droplet generated here will interact with the particle of the powders coming here from a ceramic particle, for example, and they mix in this zone easily, giving rise to uniform distribution of particles in the matrix. Here you see this is around 30 kg of billet made by us by spray forming, and here you can see we change the powder flow rate in 3 different zones. Up to this point, for example, we had 1 powder flow rate, then we increased and then further increased. Okay, so here you can see this is the billet radius and the SIC distribution. The composition of SIC volume fraction is in the bottom, it is this, then this, then this. You can see, and almost uniform. Almost uniform. Here there is an issue because it was the last point to be deposited. So here there is a different composition, but otherwise uniform distribution of particles. And here you can see the distribution. It's very well observed that this is uniform distribution of even smaller size particles of 17 micron. We have seen this for 6 micron also, but in 6 micron there was some segregation because some segregation at the triple boundaries of the grains. And now we come to spray forming of nanocrystalline materials. Amorphous and nanocrystalline materials. If you are aware that amorphous material is defined as, for example, this is a melt, and this is melting temperature. Melt is coming, and at melting temperature solidifies and in crystalline form. But if the liquid melt is not allowed to solidify and crystalline, the liquid is undercooled. That means temperature, this is melting temperature, below that the material is cooling below the melting temperature, and we call it supercooled liquid or undercooled liquid. So if we are not allowing the material to crystallize and the temperature is going down, down, down up to this point, for example, here the viscosity of the liquid is so high that it is simply impossible for the material to crystallize. And then we say this is the glass. Glass has formed. That means glass will have a structure similar to liquid. Okay, so just say melt spinning. In melt spinning, the cooling rate is so fast that you do not allow the atoms to come together and make a crystal. Okay, so but in that case, what happens that the nuclei size is not formed at all, and the thickness of the sheet is 50 micron. But if you want to make bulk materials, then what to do? Here you can see this is the conventional glass, where if this is a C curve and this is temperature, this is time, and if you are cooling a material, so here the transformation starts of crystallized. But if you are cooling at a very fast rate, then the liquid will remain liquid and only its viscosity will increase. Then you get a glassy material. Okay. But depending on the composition of your material, if the composition you change and you shift the C curve to right, then what happens? Here, at this cooling rate also, for this composition, this C curve, you can get glassy material. And if you can shift the C curve further, then at a very, very slow cooling rate also, you can get a glassy material. That means when cooling rate is determined by the thickness of a material, because very thin material will be cooling fast, but if you have thick material, it will cool slow. So if slow cooling also can give rise to a glassy material, then that means you can have thick glassy material, and this is called bulk metallic glasses. We use spray forming for such materials, and here these are the 12 millimeter thick materials we can get. This is not fully glassy, but we got at around more than 60% glassy material, amorphous material in this. This composition, what we use here, if we use powder milling, alloying, ball milling or mechanical alloying or rapid solidification, then we can get 100% amorphous material, but by spray forming up to 12 millimeter, we could get around different fraction and different distances. At the bottom, we could get around 90% amorphous material, but as we increase at the top, it will reach to 60% amorphous. But why is it possible? Because the interface what we have here, just to make interface more and more conductive, and the substrate to have more and more heat capacity, what we did that we generally people cool the substrate, we heated it to around 200 degrees centigrade, and after heating, the interface cooling will be slow as the spray comes. So we will have good conductivity or good conduction of heat from here to here, so faster cooling. And once heat is coming to this, we have to have very high heat capacity. The temperature of the substrate doesn't increase much. Okay, so these two things we did, and this is why we got such fraction of amorphous material in this. Here you can see these are cast materials and spray form. Here you can see these are featureless areas, and featureless means it can be nanocrystalline as well as on amorphous phases. And we saw this. TEM here in this area, aluminum becomes nanocrystalline. This was nanocrystalline, and these area are amorphous. Here, diffuse ring of things we see. Here you see, and this is similar. This is similar to this in 2001. This was made by powder metallurgy, where powder of the same composition was made and sintered. So here you see same kind of amorphosity is seen, but this was for rapid solidification, and in spray forming we have very slow cooling rate compared to that. And why this happened? Here also you can see this is fully amorphous area. In the deposit, this is nanocrystalline. Why this happened? Because from automation zone, when the droplets start cooling down, so it undercools, and then after some time it starts solidification, and after solidification it fully solidified. Okay, and very small droplets, if they undercool, then they may be solidified in undercooled state, in liquid state itself, because of high viscosity. Okay, so very small droplets will be in amorphous state, but larger droplets will have this kind of a structure. So here you see a liquid droplet, how it makes a journey: hot, undercooled, solidification starts, recoalesce, and then solidified fully, if we do not have a substrate. But if we put a substrate here, then what happens? The semi-solid droplet will come and make a splat, and all the undercooled liquid, being a splat, will have a very high cooling rate, and that gives the amorphosity in the deposit. So this was published in 2012, I think, by us. Okay, now we go to spray forming by quasi-crystals. I think I will take 10 more minutes. So quasi-crystals generally are defined by long-range order. These are not amorphous, neither crystalline, and they have high hardness but low toughness, and they are highly corrosion resistance, and they have low coefficient of friction. And generally they are synthesized by conventional solidification. It depends upon the composition: rapid solidification, mechanical alloying, physical vapor deposition, electrode deposition, or something like that, laser ablation. So they had not been tried by spray forming, and bulk stable quasi-crystals was determined for this composition. And how it used to happen is that I read one review article in 2004, and it suggested that the greatest challenge for the future of this is the production of industrial quantity of good quality quasi-crystalline powders and coatings, as well as of bulk materials thereof, to reach the expectation of 20-year-old quasi-crystal optimism. So here, from this statement of the review article, I saw the phase diagram and see that if copper and iron in this range, then you can have quasi-crystal in this region. Then there was an idea that, okay, if we do spray forming, then this condition can be achieved because we get rapid solidification effect in spray forming also. And then in 2005, we used spray forming to get this composition, this spray form material in one go. And here you see, in 2001, people tried to use aluminum copper iron composition to make quasi-crystalline with stepped mold. Here this is 3 mm diameter step, and the structure here was this for aluminum copper iron composition. And after heating this at 750 degrees centigrade for 3 hours, we get single phase quasi-crystal. Okay, for 3 millimeter, we have to be careful. At 3 millimeter diameter, we are getting single phase after heating at this temperature for 3 hours. Now in the spray forming, we made around 40 kg of this single phase material by spray forming, and you see these are the powders. Means once you deposit, some powders go out and they do not come on the deposit, okay, on the substrate. So the powder we collected and we saw that what is the phases, then we could see there is one phase coming up in all the powders. All the powders, they solidified at a very high cooling rate, but 40 kg of deposit will solidify definitely at a slower cooling rate. But you see what happens, 40 kg, this spray cast material, this gave a single phase material. So we fulfilled the demand of that 2004 review paper to make the single phase bulk material of 40 kg. And we did not take a single place. We took a material and a bulk material and we we took from different places, and in all the places the XRD deflection was same. That means we got a single phase bulk material. Okay. And here you can see this is single phase, but we are able to see the grains. There is no intermetallic phase as we saw earlier, and the composition distribution of aluminum, copper, and iron is uniform throughout. Okay. Now this is the last material, high entropy alloy. We use high spray forming to deposit around 20 kg, 23 kg of billet here by spray forming. This is the first time we made such a big material, big billet by spray forming. Before that, I think to the best of my knowledge, nobody did try to use high entropy alloy by spray forming. And this is the coarse grained microstructures of as-cast material. Here you see the grain size 600 to 1000 micron. And here you can see the fine structures 25 to 35 micron is in spray form condition. So here also we got highly refined grains after spray forming. Here I just want to give one indication that here you can see this area and this area. So there are some things, some microstructural features coming in these two regions. This is as-cast material and this is spray form material. And this is a distribution of copper. And here also this is a distribution of copper. So in as-cast material, you can see more amount of copper is being seen in white color. But in this, it is not. That means much of the copper in the spray form material was in solid solution. And this gives rise to a possibility that you can work with this material to get more precipitation effect in the course. And here you can see this is the EBSD of as-cast and spray form material. And here you can see this is BCC phase, this is FCC phase, and here you can see this violet color base. Violet color base, that everywhere, that means it's a single orientation of a grain in this size. Here, different grains have different orientation. That means in this area, we have so many different grains. That means there is a tremendous amount of grain refinement in spray form material. We also did some kind of heat treatment, and this gave the possibility that spray forming of high entropy alloy and heat treatments can give rise to a number of possibilities of new alloy development. With this, I thank you all. So the message is think calmly, build a strong foundation and turn this foundation into wings. Thank you very much.